Hello everyone, welcome all of you for this course on advanced NMR techniques in solution and solid state. I am Professor Surya Prakash and also chairman, just recently retired from NMR Research Center, Indian Institute of Science, Bangalore. So, we will be interacting together for the next couple of weeks. I always welcome all of you to talk to me or correspond with me in the email given in the first slide. Most of the time I will be able to respond to your queries if there are any. Okay, we will start with this course. First thing is, there is a prerequisite for this course on 1 and 2 dimensional NMR spectroscopy for chemists, which was given last year. It was again a 12 weeks course, and of course it is being rerun now. And I think this course, if you have attended, it is well and good. It is a prerequisite, I would say. Although it is not mandatory, but it is advantageous. The reason is, in the first first week or at least 1.5 weeks, I will be covering some of the fundamentals which I introduced in the last course. Though not in detail, to some extent I will be covering right from fundamentals of NMR spectroscopy and about NMR parameters, analysis of the spectrum of proton and other varieties of heteronuclei. And some of the things you would have already exposed to this in the previous course. Nevertheless, I will slightly give a brief introduction to many of these things before we go to the advanced topics. The question is, what are the advanced topics which I am going to cover in this course? In this course, I am introducing Fourier transformation, which is one of the essential prerequisite for NMR spectroscopy. It is an essential mathematical tool which we always use. Invariably you require this, and I will be talking about Fourier transformation. And of course, in the last class I discussed about chemical shift and coupling evolution, which I am also going to introduce this time, but I am going to tell you something about how it evolves in different pulse sequences, or when you apply pi pulse in different axes, what is going to happen. So, in that connection I am going to discuss about pulse phase and receiver phase. I will be talking about phase cycling and coherence transfer pathways. How do you select the coherence transfer pathway and how do you do the phase cyclings? Then I will introduce pulse field gradients. How can we use pulse field gradients to select coherent pathway? While analyzing the spectrum of coupled spins, especially the proton spectrum, it is possible to analyze in the first order way, first order analysis. It is feasible most of the weakly coupled spin systems, but of course there is also quantum mechanical way of getting the chemical shifts and coupling constants in addition to intensities of the transitions. So, I will be introducing quantum mechanical analysis of coupled spin systems. If not for all the spins, at least for 2 coupled spin systems, I will be trying to introduce AX, AB and A2 spin systems. I also want to introduce product operators, and these product operators are very useful, which with this product operator you can understand how the magnetization evolves at different parts of the pulse sequences. As you know, NMR is full of pulse sequences, varieties of 2-dimensional and 3-dimensional pulse sequences, both homonuclear and heteronuclear. And if you have the knowledge of product operators, you will be able to understand how the magnetization evolves in different pulse sequences at different points of the pulse sequence. And continuing further, I will also be introducing relaxation mechanisms, which I guess last time I tried to introduce, but I could not complete because of lack of time. So, this time I will be talking about relaxation mechanisms, T1 and T2 measurements, nuclear override effect concepts, pure shift NMR, multiple quantum NMR, and I also would like to talk about high resolution NMR spectroscopy in solids, where I will be introducing magic angle spinning, cross polarization and multiple techniques. All these things of course may not be the same order, depending upon how we are progressing with the course. I will be taking up many of these advanced additional topics in this course. Now, let me start with basic concepts of NMR spectroscopy. This is for the benefit of those people who are attending this course, who did not attend my previous course, where I was giving fundamentals of varieties of things in NMR, including analysis of the spectra. But I would like to quickly introduce in couple of classes basic concepts. Well, let us start with spin angular momentum and magnetic moment. These are the two important concepts which we require to understand NMR spectroscopy. Let us start with angular momentum. A rotating object possesses angular momentum. Different types of angular momentum you can think of, especially when we look at rotational angular momentum of atom or molecule itself, orbital angular momentum of electron, spin angular momentum of electron, and also the spin angular momentum of nucleus itself. Varieties of angular momentum you can think of. Let us focus on the spin angular momentum of subatomic particles, or otherwise elementary particles. There is a subtle difference between these two, but let us not worry about it. Look at it, we have, if you consider an atom, we have proton, neutron and electron, all the three are present. Protons and neutrons are present in the nucleus, electrons are surrounding them. But if you look at this slide, you will see protons and electrons have charges which are opposite in sign, neutron has charge 0, but all the three particles have spin angular momentum I, which is half. Half is the spin angular momentum for all these fundamental particles. Now, what is a spin? Spin is a quantum mechanical concept. There is no classical analogy for it. It is not produced by the rotation of the particle. It is an intrinsic property of the particle. That means it is always there, always present, even at absolute 0 K. 0 K it is present. You cannot question why it is there. It is there, and we have to accept it. So, spin is a nature's gift for us. Then the question is, why do we call it a spin if it is not produced by rotation of the particle? Because it is disguised by equations treating angular momentum, which is P, and it is a vector. Okay? So, this is the reason why we call this spin angular momentum as spin, although classically we talk about rotation of the particle, about its own axis and varieties of things we talk, but in reality it is because it is treated by the equations governing spin angular momentum, it is called a spin. Now, let us look at the spin of a nucleus. The spins of individual protons and neutrons combine to give an overall spin for the nucleus. This is called spin quantum number I of the nucleus itself, not individual particles. It is the total spin angular momentum of the nucleus. In the diagram what I have shown, we have green balls and a magenta color balls. You can consider one of them as protons, others are neutrons. So, they somehow assemble in the nucleus in such a way, pair themselves and give rise to total spin angular momentum for the nucleus itself. Then one can ask a question, do all nuclei of all elements or isotopes of elements possess spin? We need to answer this question. Of course, there is an empirical rule to predict NMR activity of a nuclear spin. If you look at this table which is given, there are actually 5 columns and 4 rows, and each of them we have written some of the properties like atomic mass, atomic number, and varieties of examples of nuclei. And in the 4th column you see the spin angular momentum of that particular nucleus or particular element or isotope of an element, and the last column tells you whether such nuclei are NMR active or not. Start with the second row. What it says, if you take an atomic mass of any given nucleus, if that is odd number, and atomic number, it can be odd or even, does not matter. For example, you take proton, proton is nothing but the hydrogen atom. In NMR jargon we call it as proton. It has atomic mass 1, atomic number is 1, both are odd numbers. Look at carbon 13, atomic mass is 13, which is an odd number, whereas the atomic number is 6, it is an even number, does not matter. So long as atomic mass is odd, such type of nuclei exhibit total nuclear spin angular momentum, which can be expressed as half integers, meaning their spin values could be half, 3/2, 5/2, etc. As you see in the last column, it says yes, that means such type of nuclei are NMR active nuclei. You can detect NMR with such nuclei. Go to the third row. When the atomic mass is even, atomic number is odd. Example like nitrogen 14, deuterium and boron 10. Nitrogen 14, atomic mass is an even number, whereas atomic number is an odd number, it is 7. And such type of nuclei do possess spin angular momentum, but their values are integer numbers. Their values of spin are 1, 3, 4 like that. Again, such nuclei are NMR active. Come to the last row, when atomic mass is even number and atomic number is also even. For example, carbon 12, atomic mass is 12, atomic number is 6, both are even number. There are 2 other examples I have given there. Such nuclei with the total spin angular momentum 0, that such nuclei are NMR inactive. They are not NMR active, they are called NMR silent nuclei. You cannot detect NMR of carbon 12 or oxygen 16. Okay, this is very important thing to understand whether given an element or isotope of an element, whether it possesses a spin or not, you can understand from an empirical rule given in this table. Okay. Next, we will look at spin half nuclei. That is what most of the time we are covering in this course. We do not go to more nuclei which are greater than spin half. Occasionally 1 or 2 we may touch, but most of the time in this course we cover spin half nuclei. And such nuclei are very easy to understand. Their NMR behavior is very easy to understand. Whereas if you go to the nuclei which more than spin half, they are very difficult to understand. Remember, the spin half nuclei have always have spherical charge distribution. The charge distribution of these nuclei are always spherical, and we call them as dipoles. That means it has 2 poles, positive charge and negative charge. So it can be treated like a tiny magnet. So spin half nuclei are called dipoles. Whereas the nuclei with spin greater than half have non-spherical charge distribution. They are not spherical. They are called quadrupolar nuclei. As you can see, there are 4 poles here. There are 2 plus charges and minus. Unlike dipole which has 2 charges, positive and negative, here quadrupoles, there are 2 positive charges and 2 negative charges. And such nuclei are very difficult to understand by NMR. Not impossible, it is difficult compared to spin half nuclei. The quadrupolar nuclei have electrical quadrupole moment, and as we go ahead I will tell you this quadrupolar interaction NMR is electric in nature, whereas all other interactions we can think of like dipolar interaction, all other things which we come across at a later stage which we are going to discuss, they are all magnetic in nature. but only thing is the quadrupolar interaction is electric in nature. Okay. So, with this let us start with some fundamentals of NMR spin physics. There are two quantum numbers which are associated with the spin angular momentum. I told you about the spin angular momentum of the nucleus. There are two quantum numbers associated with that. One is the spin quantum number, other is a magnetic quantum number. And this magnetic quantum number m has a constant magnitude and also direction. It is a vectorial property. It has a vectorial property, and these two quantum numbers determine the properties of the given nucleus. So, if I consider a nucleus, if I want to find out the spin angular momentum, I need to know its spin quantum number and I need to know its magnetic quantum number. If I know this, then I can define the properties of this nucleus. So, we can also calculate the magnitude of the nuclear spin angular momentum P, and it is given by spin quantum number I by a simple equation P, which is h cross into root of I into I plus 1. I is the spin quantum number, h cross is the Planck's constant h divided by 2 pi, and P is spin angular momentum. And if I take the spin angular momentum or angular momentum, it is, I can find out the component of it along z axis, and it is governed by what is called the magnetic quantum number m. What is magnetic quantum number? I will tell you, it depends upon, see, the z component of the angular momentum P is given by m into h cross. It is quantized. The see, the angular momentum along the z axis is always quantized, and it is given by Pz equal to m into h cross. What is m? M is a magnetic quantum number which depends upon I, spin quantum number, which we are going to discuss now. So, the magnetic quantum number depends upon spin quantum number, and how it depends? The value of m goes from minus I to plus I, incremented in steps of 1. For example, I say spin is equal to 1, start with minus I, minus 1, increment by 1, 0, and then 1 plus 1. So, minus I to plus I, how many we can have? There are 2 I plus 1 possible orientations. Depending upon I, the magnetic quantum number can have 2 I plus 1 possible orientation. And the z component of the spin angular momentum is quantized in a given magnetic field B naught. Okay. Now, we can find out what are the possible orientations for different spin quantum number I. For example, I will take spin half nuclei. There are two orientations for spin half nuclei which correspond to minus half state and plus half state. You can find out m goes from minus half, say minus I to plus I. There are only two possible orientations, minus half and plus half. For spin half nuclei, there are two orientations. For spin 1 nuclei, as I told you earlier, there are three possible orientations, minus 1, 0 and plus 1. What about spin 3 by 2? There are 4 orientations. Starts with minus 3 by 2, minus half, half and 3 by 2. There are 4 possible orientations. Now, we can find out the quantization directions of the magnetic quantum number. I know what is the magnetic quantum number, I can find out the quantization direction also. This, for example, for spin half nuclei, since mi can take only two values, as I said, plus half and minus half. For mi which is equal to plus half, the spin angular momentum orients in the direction of the field. For mi equal to minus half, the spin angular momentum orients opposite to the direction of the field. But here you should know, in the direction of the field means it not exactly aligned along the field. It makes at an angle theta, which you can understand if you go more into the details of this, which I covered in the last course. So, I am not going to touch upon those things. But please remember, you can find out the angle theta at which these orientations are present. We can find out those things. Let us consider two spin states for spin half nuclei, mi equal to half or minus half. Plus half is called a spin up state nuclear spin is in the direction oriented parallel to the magnetic field, minus half is spin down state. And conventionally spin up state is called the alpha state and spin down state is called the beta state. Please remember, in rest of the course wherever possible I will be using alpha state, alpha, alpha, beta, beta, varieties of terms I will be using. Always remember, when I consider spin off nuclei, alpha is spin up, beta is spin down state. Okay. Now the direction of the orientation and magnitude of the spin angular momentum for spin off nucleus can be found out by a simple equation. Of course, as I told you, it is making an angle theta, and if I consider spin angular momentum P, I told you in the previous slide, which is equal to h cross into root of I into I plus 1. Now the z component is also quantized, which I said also Pz is equal to m into h cross. Now you know two sides of the right angle triangle, and I can find out what is the opposite side, and I know what is theta. So I can find out theta knowing these things, and if I find out cosine of the angle theta, which is given by mh cross over h cross into square root of I into I plus 1. This for spin, this for magnetic quantum number m equal to half, and substituting all these values and calculate, you can find out what is the angle theta. Theta turns out to be cosine inverse of half over root of 3 by 4, which if you calculate turns out to be 54.7 degree with respect to z axis. This is for m equal to plus half. What happened for m equal to minus half state? Again, you can put these parameters and find out it is same 54.7 degree, but it is in the direction opposite to the magnetic field, that is in the minus z axis, towards minus z axis, or in other words, if you consider from plus z axis, it is 125.3 degrees or 54.7 degree from minus z axis. So with this, let me introduce you a new term called nuclear magnetic moment, mu. Now if I consider the charged nucleus, the charged nucleus rotating with angular velocity or angular frequency, no sorry, not angular velocity, angular frequency omega, which is given by 2 pi into nu, it creates a magnetic field B, and this is the way this nucleus will be, let us say, undergoing spinning, because it is a charged nucleus, let us say. Then it generates a magnetic field. It can be treated like a tiny bar magnet. As I told you, spin off nuclei are dipoles. It can be treated like a small tiny bar magnet. It is analogous to that, where the axis is small bar magnet. You consider the axis of the magnet is coinciding with the spin rotation axis. So nuclear spin is like a tiny magnet. Now when you say, since nuclear spin behaves like a tiny magnet, whenever you have a magnet, you would have studied in your school, we can define what is called a magnetic moment. Since a dipole, we can call it as a magnetic dipole moment, which is given as mu. We can define it, we can find out these things, okay. And this mu is a vector. Please understand, please remember this mu is a vector, which we try to understand as we go ahead further. So magnetic moment mu is proportional to spin angular momentum P. Mu is equal to gamma into P. Gamma is what is called a proportionality constant. It is called a gyromagnetic ratio. It is constant for a given nucleus. For different nuclei, gamma are different. And substitute for P in mu. I knew what is P. I already told you P is equal to h cross into root of I into I plus 1. You substitute that, then mu becomes gamma into h cross into root of I into I plus 1. Okay. Now what will happen if I is 0? If the magnetic moment, spin angular momentum is 0, mu is 0. That means magnetic moment is 0. And this is, remember, this magnetic moment is very, very important. It should be present. That means spin should be present. Only then the magnetic moment will interact with the external magnetic field. As I go further, I will tell you for observation of NMR. So I must be present to to see NMR. If I is equal to 0, then no magnetic moment and no NMR. And gamma value is constant for a given nucleus. Different nuclei have different gamma. And for example, for protons, its value is some number 26.75 into 10 to the power of 7 radians per Tesla per second. Magnetic field is always expressed in Tesla. 1 Tesla is 10,000 Gauss. Similarly, for carbon 13, its value is 6.728 into same 10 power of 7 into 7 radians per Tesla per second. These values for all the nuclei, these gamma values are known. Okay. So, now interaction of different nuclei in the given magnetic field we can find out. Angular momentum P is quantized, I told you. That means mu is also quantized, because mu and angular momentum are related to each other, I already told you. So, mu is also quantized along z direction in the presence of an external magnetic field. So, I would call mu is equal to gamma into Pz. What is Pz? Pz is equal to h cross into m, that is what I told you already. So, z quantum of the angular momentum is quantized, which is equal to h cross into m. So, its value also depends upon the magnetic quantum number m. So, the magnetic moment mu, its value depends upon magnetic quantum number m. So, gyromagnetic ratio also depends on charge and mass of the nucleus. It is given by gamma is equal to E by 2 m into c. E is charge and m is mass, and of course, c is the velocity of light. So, nuclei with higher mass have lower gamma. Remember, mass is coming in the denominator there. As the mass keeps increasing, gamma value keeps coming down. So, the nuclei with the lower mass will have higher gamma. So, if you look at this, we will go further. Mu z we can say equal to gamma into Pz, which is equal to gamma into h cross into m. That is what I already explained. Now, mu z has different values for different nuclei, because gamma is different, as that is what I told you. So, the nucleus, for example, some nuclei may have the same spin quantum number, I may be same, I may be half. When I is equal to half, magnetic quantum number m also should be same, because it can take only from minus half to plus half, only 2 possible values. So, if I is same, m is same for different nuclei, then what makes them different? What makes them different is gamma. So, with this, let us take an example of two nuclei, proton and carbon 13, two isotopes, carbon 13 isotope and proton. Proton is hydrogen atom. I is equal to half for both of them, spin is half. When I say spin is half, I already told you mi equal to minus half and plus half. There are two possible orientations. So, what about gamma? Put the value for this in gamma. Gamma is equal to E over 2 into m into c. I is same, m is same, but what about mi is same, what about mass, which is coming in the denominator? They are different. As a consequence, if you go mu is equal to gamma into p, for proton and carbon 13, they have a different magnetic moments, although they have a same spin angular momentum, same spin quantum number, same magnetic quantum number, their magnetic moments are different because gammas are different. That is the important thing. So, please remember, all nuclei with a different gamma can be individually studied by NMR. Okay. So, these are the characteristics of some of the selected nuclei. If you go into the periodic table, all nuclei, at least one element of each nuclei can be studied by NMR. Some of the important nuclei which we study both in organic chemistry, biochemistry, biophysics or inorganic chemistry, I have listed here. Look at this one, isotope, proton, natural abundance is 99, spin is half, its magnetic quantum number is 2.79, then is 26.75 is the gyromagnetic ratio into that unit which I have given in the top. Look at the carbon 13, its abundance is, spin is half, abundance is 1.1, its gamma is 4 times less than that of proton. Similarly, as you go further, some of the nuclei will have a negative magnetic moment. For example, silicon. Look at silicon, second row from the bottom, its magnetic momentum is negative. So, gyromagnetic ratio is minus 0.5, I am sorry, minus 5.3. All these parameters have some meaning in it. We will go, as you go ahead further, we will understand these things. Okay? So, these are the things which we have to understand, but please remember commonly studied nuclei in chemistry and biology are proton, carbon, nitrogen 15, phosphorus 31, all of them are spin off nuclei, and also deuterium which is spin 1 nuclei. Spin half nuclei are relatively easy to study, and there are other nuclei like boron, boron 11, boron 10, aluminum 27, oxygen 17, etc. These are studied in inorganic chemistry and material science, etc. I think now the time is up for the day. What I am going to stop is, I am going to do is I will stop here. So, what we did discuss today is the fundamental concept of spin physics, about spin angular momentum, spin quantum number, magnetic quantum number, magnetic moment, how they are related to each other. We calculated the magnitude of two possible orientation for spin off nuclei, and we also found out the difference between two nuclei which are same spin quantum number, spin magnetic quantum number, but they have a different gamma which can be studied individually. And we also saw different properties of different nuclei which based on their abundance, spin, gyromagnetic ratio and magnetic moment. Some of them have positive magnetic moment, some have negative magnetic moment. They have a different meaning which I am going to discuss in the subsequent classes. But these are the concepts which we understood. Next, we have to understand what happens if we take this such type of nuclei and put it in a strong external magnetic field. What is going to happen? That is a new type of interaction called Zeeman interaction, which is the basis to study NMR. So, in the next class we will discuss from Zeeman interaction and go further. Thank you very much.